In section 1.5, we're going to be looking at transformations of functions, and there's a couple different transformations that we can do, so we're just going to kind of take them piece by piece. Again, I want to show you, like we did in the previous section, I want to show you some generic abstract of what's going on with this, and then I want to go into some more details. We're going to look at examples. I'm going to show you graphically what's going on with it so you can picture what's going on. Although we don't use the graphing calculator for this, it's good to know pictorially how it's moving around because you will have to use graph to create equations based off those transformations. Lots of talk, let's just jump in here. So the first one we're going to look at is shifts, and we're going to be looking at a translation or a slide. And there's two different shifts that we can look at: a vertical shift of moving a function up and down on a graph, and a horizontal shift of moving a graph left and right from the origin. Now what we're doing is we're basing it off of our parent function that we've already analyzed in previous videos. We're looking at those very basic parent functions and we're moving them around, and it basically shows us how these more complicated graphs will look or move based on what we know about our parent functions paired with what we're doing here with transformations. So first, let's just kind of start out generically. So this would mean, let's just kind of number it. Number one, if we have, say, our function and we add some c to the outside of the entire function, adding that value on the outside is going to move your graph up c units, whatever that may be. So let's do an example so you can kind of see what's going on with the equation, but also with the picture. Say my function was the parent function x squared, and I just added a plus 3 on the end of that parent function. Well, remember, your parent function is something like this. This is a quadratic. I'm just going to rough sketch it over here. Well, if I add on this plus 3 to the end of it, that means it's going to move it up 1, 2, 3. And so then it would create this new graph up here, and this would be x squared plus 3. So it just moved all your points up 3 units. Now, if we look at the second way this vertical shift can happen, it could be if you had f of x minus c, and that is what's going to move it down c units. And so that would be f of x equal to x squared minus 3. Let's look at that one. Let me switch colors here so we can notice the difference between them. It's going to take your parent function, which we could see was in the middle, and move everything down 3 units. So 1, 2, 3. You can see it's still that U shape. It's still symmetrical over that y-axis, but it just shifted everything down 3 units. And so having the addition or subtraction of a number on the outside of that parent function is what's going to move your graph up and down. Now, if we go into this and we look at the horizontal shift, we're going to have two different shifts. Say we had f of x plus c, and we're adding a value inside that parentheses. Then that's going to be c units to the left. And so if you think about this, it's the opposite of what you would think. If you took that x plus c and say it equal to 0, subtract the c over, you would get x equal to negative c. So if you look at an example of this, say we looked at f of x equal to absolute value of x plus 2. Well, your absolute value graph is a V shape at your origin. I'm just rough sketching here. So if I do plus 2, it's going to move the opposite of what I think, so it actually moves it left 2 and gives me a V shape like this, and this would be the absolute value of x plus 2. And again, this was just our parent function. Now, if I want to move the opposite direction, this would be number 2, f of x minus c. This would be c units to the right. And so again, if you think about x minus c equal to 0 and solving for x, that's going to be the opposite of what you think. So this would be like f of x equals the absolute value of x, say minus 2. I'm going to switch colors again. So now we're going to go to the right 2, and again, on the inside, it's the opposite of what you would think movement-wise. When it's on the outside, it's exactly what you think. So we're now able to move our parent functions up, down, left, and right. Let's move on to that next transformation, and that is a reflection. Now we're going to have two different reflections. We're going to have a reflection of the x-axis and a reflection of the y-axis. And just like your shifts, it's all about the placement. If you have a negative applied on the outside of your function, say for an example, if you had f of x equal to negative square root of x, that is going to give you a reflection on the x-axis. And so first, let's do like we did before, and let's look at the parent function. So here is the square root of x. So if I apply the negative on the outside, it reflects over the x-axis, and I get this one, which is negative square root of x. And so if I apply that negative on the inside of the function, for example, f of x equal to the square root of negative x, that gives us a reflection on the y-axis, and so that would flip that blue graph over here into this quadrant, and that would be the square root of negative x. So with these transformations, it's all about the placement of whatever you're doing. You know, if it's on the inside, that's your horizontal movement. If it's on the outside, that's on your vertical movement. And so knowing those different placements are going to be handy as you work through these assignments. So as we begin to talk about reflection, that's a nice transition into our symmetry. When we're talking about the symmetry of the function, you know, you're trying to think about where could you fold it in such ways that it would give you the exact same picture on the other side. So there's two types of symmetries that are going to do that for you. There's the even function and there's an odd function, and based off those functions we can see the symmetry. And so if you have an even function, this is going to dictate to you that you have y-axis symmetry. Now we're going to have to do a bit of a calculation in order to figure this out, but it means that if we have f of x and we apply a negative throughout those x's, that we end up with the same function. And so what you're going to do is you're going to have to do some calculations to figure this out if it's a function you don't know graphically what it looks like. And a hint to this would be to replace x with negative x and see if you get the same function. So let's do an example. Say we have the function and it says, is f of x equal to x squared plus 4 an even function? And so we go, okay, is it an even function? And so in order to fill that out, we check it and we say check, is f of negative x, that would be equal to applying a negative x everywhere you had a positive x. Well, you can see that when I take negative x and square that whole thing, that outputs a positive x, which is what we started with. And so since that is the same as the original, it is even. And you can see this by looking at the function as well. This is a quadratic moved up 4, 1, 2, 3, 4. You can see that it is symmetrical over that y-axis, going back to what we know about quadratics with axis of symmetry, etc. But this little part in here of calculating it is going to show you if you have an even function and if you have this y-axis symmetry. So let's look at an odd function. An odd function is going to have origin symmetry. And so that means it's going to be flipped over x and y. And so how do we check for this? We're going to say, is f of negative x equal to negative f of x? So can I apply that negative on the outside and inside and it output the exact same function? So let's do an example of that. So it says, is f of x equal to x cubed plus 2x an odd function? And so we're going to check. And so I'm going to say f of negative x. So that means I'm going to apply a negative x everywhere I had an x in the original. And so I'm going to say negative x cubed plus 2 times negative x. So that would be equal to negative x cubed would give me 3 negatives still when I cube it. 2 times negative x would be minus 2x. And If I factor out a negative out of both of those terms, I end up with x cubed plus 2x. And so you can see that this is the opposite sign of the original function. So that's like negative of f of x. And that's what we were going for here, showing that those two are equal. So you can see here I am plugging it in, and by the time I cleaned it up, it turned out to the other one. So this shows me that it has an origin symmetry. And we can see that just to kind of show you what's going on a graph. Not that we need the graph, but this would be something like this. And so you can see that it looks like it has been flipped over the x-axis and flipped over the y-axis. So knowing your even and odd functions is going to help with figuring out what are your symmetries of that function. And again, it's going to take the calculations of plugging in both of those. So we've got transformations shifting up and down, left and right. We did some flipping, which brought in our symmetry. And now let's begin to stretch and compress these functions. Now, I would say when you're working through the homework, the stretches and compressions can be the most confusing because it's about placement, and they are really specific about, is this a vertical stretch? Is this a vertical shrink? So of all the notes we have taken so far, these would be the ones that I would need to go back to where I'm working the homeworks. But then when it comes down to working the exams, I try to pick specific questions that are not going to have to tell you vertical stretch or shrink, but in the exam it would tell you, is it stretch / shrinked? Just knowing that it was changing in width, not necessarily being able to memorize that detail of vertical or horizontal. Okay, so let's work through this. So if I have a vertical stretch or shrink, that means I am taking a function and I am multiplying something on the outside of that function. That multiplier on the outside of the function is 1 going to be a stretch when c is greater than 1. So for example, if you had 3 absolute value of x. And then it is going to be a shrink when c is between 0 and 1, such as a small fraction. So that would be the example of like 1/3 absolute value of x. Now graphically, that means that we are going to take, here's our absolute value of x. If we are looking at the 3 being multiplied, we're going to see a stretch on it. So it's going to be a little bit slimmer. And if we were looking at a shrink on it, it kind of is like you put your hand on it and pressed it down. So it's getting wider and wider. And so this would be that 1/3 being applied. And this would be the 3 being applied. And so just kind of interesting there. Now, the reason I say this is something you're going to have to go back to and use this notes as you're working the practices or homeworks is because when you go to horizontal, you're looking at g of x being equal to f of c of x when you have the multiplier inside of the function there, or the parentheses, or in this case, absolute value. They switch up their wording and they now say that it's a horizontal shrink when c is greater than 1, such as if you had the absolute value of 3x, so moving that 3 inside. And they're going to call it a stretch when c is between 0 and 1, or that fraction, so like the absolute value of 1/3 x. Oh, accidentally too more. So this is confusing, but I'm going to tell you this little piece of information from your notes, you do want to recall this as you're working your practice. And again, I'll narrow it down and make it more generic as we move to the exam, so you don't have to recall that because we don't use any notes on our exams. And so graphically, let's go ahead and kind of draw that out, sketch it over here to the side. So that gives you, here's the absolute value graph. And so if I put this 3 right here on the inside, this is a horizontal shrink. And then here's your 1/3. And so you can see the graphs are similar, but we're switching that wording of stretch and see. So I definitely agree that it can be confusing. Use this little last bits of notes as you're working through the practices, but as always, reach out to me if you need additional help.